The most difficult part of applied machine learning is not importing software libraries. It is figuring out how to mathematically represent messy human problems. To understand how this works in practice, we are going to look at a recent cohort of machine learning capstone projects. These students tackled real-world issues, ranging from human stress and attention spans to credit card fraud. The raw data varies wildly. Some rely on simple surveys collecting text responses, while others ingest high-speed streams of numerical credit card transactions. You cannot feed a trickle of opinions and a flood of financial logs into the same algorithm. As the scale and shape of this data change, the underlying architecture must shift to accommodate it. We can map this relationship using an analytical framework called the algorithm selection matrix. The x-axis measures data complexity and volume. The y-axis measures interpretability versus predictive power. By reverse engineering these actual student projects onto this coordinate plane, we can build a clear, logical tree for selecting the right model for any tabular dataset. Before we can plot a single algorithm on that matrix, we have to solve a critical data bottleneck. Several of the capstone projects, like the ones analyzing mental health and stress, relied entirely on qualitative human surveys. Algorithms process math. They cannot compute textual or categorical descriptions like high stress or poor sleep. This introduces a mandatory architectural step known as categorical encoding. We transform subjective text into numerical representations. Sleep quality poor splits into a one-hot encoded binary array 0, 0, 1. This sequence functions as a mathematical vector. The text vanishes, leaving measurable coordinates. This expands the dataset horizontally into a wide machine-readable matrix. Proper numerical translation is the absolute foundation. If you do not resolve your categorical data, no algorithm can be trained at all. Now, look at the lower left quadrant of our matrix. This zone represents data problems with low complexity and a strict binary output. This is where we plot the stress prediction project. The structural parameters here are highly constrained. The student gathered a very small dataset of exactly 50 responses, aiming to predict a simple yes or no target. Is the student stressed or not? For this exact data topology, the optimal baseline model is logistic regression. This scatterplot shows how logistic regression works. It draws a clean S-shaped sigmoid curve right between the data clusters. That curve establishes a straightforward probability threshold. If the calculation lands above the curve, the student is stressed. Below it, they are not. Deploying an advanced heavy-duty algorithm on a dataset this small introduces immediate risk. A complex model will overfit. Instead of learning the underlying pattern, it will simply memorize the noise and quirks of those specific 50 data points, making it useless for predicting new instances. When the relationship between your input features and your target is assumed to be linear, simplicity is an engineering advantage. Linear models like logistic regression are the most effective choice when your target is binary and your data volume cannot support complex mapping. Let's shift our focus to the upper right quadrant. Here, we encounter high-complexity, nonlinear tabular data. This zone is built for projects like the attention analyzer and customer turn prediction. This data is inherently chaotic. Features include varied subscription lengths, diverse media content types, and customer service interactions. This is where linear models mathematically fail. Human behavior is unpredictable and nonlinear. A single, clean curve cannot possibly map all these competing variations. To process this, we require an architectural upgrade to ensemble methods, specifically the random forest algorithm. Random forest routes chaotic tabular data through multiple independent decision trees simultaneously. Each tree analyzes a different data subset and casts its own distinct vote on the final outcome. These separate predictions are then aggregated into a single majority vote. This ensemble voting mechanism is crucial because it effectively smooths out the unpredictable noise inherent in individual human variables. When dealing with messy, multivariable human behavior, random forests deliver the required nonlinear flexibility without needing excessive manual tuning. We now move to the absolute apex of the matrix, high-stakes real-time inference. This is the domain of the real-time fraud detection project. The engineering constraints here are extreme. The model processes live Kafka data streams and faces massive data imbalance because actual credit card fraud is incredibly rare compared to the millions of normal daily transactions. To handle these specific constraints, we use XGBoost, which utilizes a technique called gradient boosting. The architecture differs entirely from random forest. Instead of building independent trees that vote at the end, XGBoost builds its trees sequentially. This process is sequential error correction. If the first tree makes a mistake, that specific error feeds directly into the parameters of the second tree, forcing it to correct the flaw. This chained correction explicitly optimizes for precision and recall. When you are trying to find a mathematical needle in a massive haystack, parallel voting is not enough. You need targeted, compounding error correction. When prioritizing precision and recall on imbalanced tabular data, XGBoost's sequential learning allows it to catch rare fraud events that other models often misclassify. This chart displays the taxonomy of tabular data topologies. Zone 1, Logistic Regression handles baseline binary outputs on small datasets. Zone 2, Random forests capture nonlinear behavioral patterns. Zone 3, XGBoost optimizes high-stakes metrics on severely imbalanced datasets. This brings us to a common misconception. Junior engineers frequently assume that deep learning and neural networks should be applied to every problem. For custom, small to medium tabular datasets, deep learning is often less efficient and harder to interpret than tree-based ensemble methods. Algorithm selection is never arbitrary. It is a calculated mathematical reaction to the raw materials you collected. A successful machine learning architecture is defined by how precisely the chosen algorithm reflects the underlying structure.